So folks, in this video I'm going to leave you to get all of the details. There's a hyperlink that links to the derivation of our arc length formula. But I'd like to run through part of it with you. So if you click that link, you should see this filled in derivation. So here is our curve, and it's sketched in blue. And our goal is to find the length of this curve between 2 points. So let's suppose if we plug in time value a into this curve, it gives us this vector right here, this red vector, which corresponds to a point P. And then if we plug in the time value b into our position function, it will give us this red vector right here, and that will correspond to some point Q. And our goal is to find the length of this curve as we travel from point P to Q. Very important, folks. What can I not do? I cannot just ask what's the distance between point P and point Q, because my curve is not necessarily moving in a straight line. And in fact, if I'm going to ask this question, it's more than likely not going to be moving in a straight line. So just saying what's the distance between these 2 points is not the same as saying what is the length, the distance that we travel as we travel along the blue curve, which is not a straight line. So what we do to help facilitate this is we think about plugging in 2 very close time values. So I'm going to plug in some t0 value, and that's going to give me this vector right here. And then I'm going to add just a little increment of t called delta t to that, and that's going to give me this new green vector right here. And so we can think of chopping up this blue curve into a bunch of different little line segments that correspond to these differences between these 2 vectors. Okay? Now, very important, the orange delta S segment that we're after, we'd like to add up all of these delta S segments, is not exactly the difference between this vector and this vector. So here I've sketched the difference between these 2 vectors is this red vector right here. And the key idea, though, is that as delta t goes to 0, remember delta t is what gave us this other green vector here. If this gets smaller and smaller, then that will move this second green vector closer to the first, and our red difference vector will be closer and closer to the change in the distance along the curve for that small time segment. So the key idea is that as time goes to 0, this different vector approaches delta S. So here we have that delta S is approximately the length. So what I'm saying here is that the length of this this orange segment of the curve is approximately the length of that red difference vector. And so then if we look at the expression delta S over delta t, be careful, delta t down here is a scalar. This is asking a magnitude of a vector, but if I bring that scalar in, then we can go ahead and start looking at this ratio delta S over delta t. So then we define delta S over delta t to be the limit as delta t approaches, careful, I was accurate in this, folks, the number 0. So as the delta t approaches the number 0, then by the observation we made here, this red vector is going to begin the length of this red vector will begin approaching the length of this orange delta S segment. But what we notice here is that this expression is just the magnitude of our derivative function. So here we have that delta or ds over dt is equal to, in limit, the magnitude of our velocity vector. I find this this is kind of a lengthy and maybe difficult derivation, folks. Please work through it a few times. But I find that if you think of solving this ds, solving this expression for ds, which is a little bit weird to talk about, treating that ds dt as for a fraction, that's maybe problematic, but let's do it anyway. If we were to multiply this differential t over to the other side, I have this expression right here. And I like writing this expression right here because it reminds me of the formula distance is equal to speed times time. Remember here, this is our velocity function, and we're taking its magnitude, so that actually is giving us speed. And so we've got the speed at a point in time times a small increment of time is equal to a small increment of distance. So finally, we're ready to derive arc length. We're going to say that the arc length can be computed by just taking all of those little orange segments, delta S. But in limit, those delta S's will be similar to our differential S's. So we're adding up all of those little orange segments as we move from point P to point Q. So we're integrating from point P to Q of ds. Okay? But this ds could just be written as ds over dt dt, and we said that ds dt is the same as our r prime of t in magnitude. So this is our formula for computing the magnitude, or for computing the arc length. Okay? Here I've made two observations. One, this is easier for me to remember. This really does remind me of going from point P to point Q and adding up a bunch of little ds long segments as I move along the curve. So this seems a little bit more intuitive than this formula, but this formula is more practical for the actual computation of arc length. So folks, at this point, what I would do now is then carefully write down this derivation, and we will talk about it more in class and answer any questions that you have then, and then join me with the next questions.